All right, good afternoon, everybody. We are moving on to a new topic. All right, topic 9. Okay, topic 9, lesson 1 is going to start on page 428. All right, 428. So topic 9 is about the Earth, Sun, and Moon system. All right, so we're going to start heading off into space. All right, so once you get to page 428, we are on lesson 1, movement in space. And I'm going to draw your attention over to page 429, and we're going to start going over some of this vocabulary. Okay, so the first term I would like to go over with you, over on page 429, is a satellite. All right, so according to the book, a satellite is a body that orbits a planet. Okay, so right away, you might automatically think of satellites, for instance, going around the Earth. Satellites used for cell phones, used for TV, used for military, to communicate on multiple sides of the planet. A satellite does orbit around the Earth, okay? So we're talking about things that orbit around the Earth. So actual satellites are satellites. The Earth does have a natural satellite, and something that is not man-made, right? It is natural. The moon, right? The moon acts as a natural satellite, orbiting the Earth. All right, our next vocabulary word is a star. A star is a giant ball of superheated gas or plasma. Now remember, plasma is that fourth state of matter. We have solid, liquid, gas, and then we have plasma, superheated, supercharged gas. Okay? And is mainly a star. The gas that's burning is hydrogen and helium. Okay? A planet. Right? A planet is an object that orbits the sun and is large enough to have become round by its own gravity. So if we're talking about, and I lost my. So if we're talking about having its own gravity and causing it to be round, so we have in any planet, right? Gravity is always strongest towards the center. We're always pulling towards that center point. That's why everything falls down, right, to the ground, because it's being pulled towards the center of that mass. The more mass we have, right, the more gravity we have. Okay? So gravity and mass go hand in hand, right? The more massive an object is, the more gravity it's going to have. Now that doesn't necessarily mean the larger an object it is, the more gravity it has, because remember, how large or how much volume an object has doesn't necessarily mean it has a lot of mass. So if I take, for instance, a small metal ball and compare that to a large blown up balloon, right, the small metal ball might have more mass because those molecules are more densely packed together, while the larger balloon would have less mass and be less dense. Right? Remember, density equals mass times volume. Okay? So our volume can be very big, but if our mass is very low, okay, that kind of cancels it out. So the reason why planets become spheres and even moons become spheres is because that gravity is pulling inwards towards the very center. Okay? As it's pulling towards the very center, it's collecting debris. Okay? And it gets bigger, and it gets bigger, and it gets bigger. Everything's still getting pulled towards that center. And as it builds upon itself, as it collects more and more debris that's in its path, as it moves, okay, it gets bigger and bigger. So a planet that's larger, let's say if we're comparing just, for instance, planets made out of mostly rock, all right, so those would be like the inner planets, Mercury, Venus, Earth, Mars. The planets that had the most in their way, all right, the most debris in their way, would essentially have collected the most rock and become bigger, right? Always becoming that spherical shape. Okay? And by doing so, they've cleared their orbit of any debris. Okay, so they've either knocked it away or absorbed it, or not absorbed, pulled it in with their gravity, and making it part of them, part of their entity. All right, so next I want to go over some more vocabulary, and I'm going to give you more than what was in the book. For instance, if we go back to the book, they're talking about meteors and comets. I want to go a little more in depth than that. So let's start off with giant, big, floating around pieces of rock called asteroids. Okay, now your asteroids are going to be found generally in our solar system. Right, so if I try to draw this to scale, probably not going to happen very well, but I'll give it a shot. So here's the sun, and then we have Mercury, Venus, Earth, Mars, a little smaller. All right, Mars, and then we have big old Jupiter. All right, I'm going to stop there because we have more planets, but that's not the point I'm trying to make here. All right, asteroids. Asteroids are generally going to be found in this area here. Just like the planets, here are also orbiting the sun. Okay, and this is known as the asteroid belt. All right, and every now and then an asteroid will get knocked out of this asteroid belt, and it'll take a slightly different course. Okay, but generally you'll find these massive rocks with maybe some ice and stuff collected in them, floating in the asteroid belt between Mars and Jupiter. Okay, so I want to go over these definitions here. A meteoroid, right? So this is like a smaller piece of rock and ice. So an asteroid is going to be pretty massive. There are smaller asteroids though, and then there's meteoroids. There's really large meteoroids, and then there's smaller ones. But anyways, these are just generally not as big as an asteroid. Okay, and you might find these places other than the asteroid belt. Okay, moving further down, a meteor. Right, this is mentioned in the book. A meteoroid, all right, enters the Earth's atmosphere, a meteor is a meteoroid that enters the Earth's atmosphere and is burning up. Okay, these are commonly known as shooting stars. So if you ever see like a shooting star zip across the night sky, that is a meteoroid, all right, falling through the atmosphere and burning up. All right, and these are called meteors. Now, if that meteoroid, if it's large enough, or if an asteroid is small enough, right, and it gets through the atmosphere and strikes the Earth's surface, this is called a meteorite. Right? The meteoroid, small piece of rock and ice, meteor, that meteoroid is falling through the atmosphere, and then eventually if it gets all the way through without burning up and it strikes the surface of the Earth, now it is a meteorite. Okay? Now, shooting stars can kind of be confused with comets. Right? So they both have like what looks like a tail. Okay? The meteor has a tail because as it's entering the atmosphere, it's literally losing pieces of itself and burning up. A comet is a ball of gas and ice floating through space, and as it approaches the sun is obviously going to heat that gas and that ice up. Right? Now it starts to lose pieces of itself. That gas and that dust is going to trail behind it. All right? And as it heats up, it's going to have kind of a glowing effect. All right, so it looks kind of like a glowing ball with a tail just kind of going through the sky. But once again, a comet is in space. Okay, meteor is entering the Earth's surface. This comet is in space. All right, so that's a major difference. All right, I want to touch upon constellations. Okay, I'm not going to spend a whole lot of time with this, but I will talk a little bit more about them when we talk about how the Earth actually moves in space. Okay, so there are many constellations in the nighttime sky. I think totally confirmed right now. It says right here 88. All right, constellations in the nighttime sky. Basically, every point where you see one of these lines end is the location of a star. Okay. Now there's many more stars around them. These aren't the only stars in the sky. However, these are recognizable as certain shapes. Now, humans, over the course of time, use these different shapes that they saw in the stars, right, connecting the dots, in order to um, rationalize, for instance, mythological stories that they had. So many of these things here, like for instance, right here, Hercules, right, the demigod from the Greek mythology, Hercules is right here. Um, and these mythological beings were used to justify these patterns, or these patterns were justified according to the stories of these mythological figures. I don't know, however way you want to say it. But for instance, a lot of these figures, like when they passed on and moved to a different plane of existence, I guess, so to speak. For instance, Mount Olympus was where they believed the gods lived in Greece, in ancient Greece. For instance, so Hercules, when he moved to Olympus, all right, upon his death, he became part of the nighttime sky, right? And that's kind of how they rationalized the shapes and helped remember the different shapes. Many humans also use different shapes in the sky, different constellations for travel, all right, knowing where certain constellations would be during different periods of the year, helped them determine which direction they were going at night. Remember, for instance, during the day, you can use the sun to travel, right? If you know the position of the sun, you can and you can determine then north, south, east, and west, knowing the way the sun travels during that time of the year, all right, where east would be and where west would be. Sun rises in the east, sets in the west. All right, so if we continue on to the movement of these stars in the sky, all right, this has to do with the movement of the Earth, all right, on its rotational axis. So as the Earth is spinning in space, okay, going from day to night, night to day, right, facing the sun, facing away from the sun, facing the sun, facing away from the sun, as it's spinning on that central point, right, from North Pole to South Pole, okay, the stars seem in the sky over time, right, to swirl around. Okay, that's because the Earth is actually spinning. Now these stars aren't moving, but they're in a fixed position. But the Earth is spinning, so it appears as if these stars are spinning. And that central star is Polaris, which is actually a group of stars, and that is a point in the sky at which our North Pole, right, points directly to. So it appears as if that group of stars right there, which looks like one star because it's so far away, does not move. Okay. Now, as the seasons change and the year goes on, you may see different things in the sky, for instance, in the spring than you did in the summer versus fall and winter. Okay. And this has to do with the Earth actually orbiting around the sun. All right, so if you go to my little diagram here that I created, not entirely accurate, but it's going to get the point across. Now, I really don't know when in the year you will see the constellation Leo. All right, this is Leo the lion. Okay, I actually took this picture right out of your textbook. All right, and in this case right here, so Leo might be found somewhere over in this section of space. Okay. Now, I have the sun and I have the earth. Now, I have this drawn certain ways for certain reasons. Right? This line going through the center is the axis. That's how the earth spins. Right? The North Pole and the South Pole aren't directly up and down. They're not perpendicular to the sun. Okay? We'll go into more about this when we talk about the changing of seasons and what causes the different temperatures as the seasons change. Okay? Now, as the earth is spinning, okay, right, spinning in this motion right here, okay, it's also traveling around the sun, okay, so one spin, so starting here, spinning around, spinning back, that's a day. All right, I have this side lit up because it's facing the sun. This side of the earth is experiencing daytime. This side of the earth is experiencing nighttime. And it'll continue to spin like this as it goes around the sun, okay, so as it goes around the sun, right, different areas of the Earth are going to experience the different seasons. Okay, I'm not going to get into that right now, though. So if we look at the constellation Leo here, okay, let's say we're experiencing nighttime. So we're on this side of the Earth. Okay, over here would be the, I'm sorry, over over here would be our eastern sky at night, and over here would be the western sky at night. So during this moment with the Earth in this position, okay, around the sun, we would see this constellation at night, right, in the eastern sky, right? But if we move, let's say, over to here, okay, so now we've moved from this position around the sun to this position around the sun. Now I have the Earth completely blue, right, because nighttime would actually be on the back side, and from this angle, it's not a 3D model, so we can't see that, okay? But on the back side, okay, over here would be the east, over here would be the west, okay? Now, if we saw Leo in the sky, sorry, I'm having a little problem here. Now, if we saw Leo in the sky, all right, Leo would be on the western side of the sky at night, okay? Whereas in over here, this side being the west, this side being the east, Leo would be more towards on the eastern sky. So as the Earth travels around the sun, these constellations can be found in different places. Sometimes they can not be seen at all. So for instance, if the Earth was over here, okay, this side's experiencing nighttime, this side's during the day. If Leo is in this point in space, okay, odds are we're not going to see Leo, because we would have to look past the sun in order to see it. The sun's so bright, this is daytime, that we're not going to see any of the stars. We're not going to see any stars, right? Rarely do you ever see any kind of stars at during the day. Usually only right as the sun, maybe as the sun's rising or as the sun's setting, maybe. Okay, so during the day you're not going to see Leo, right? You only see Leo at night. So there are certain constellations that during certain points of the year you may never see at all. And it's not until a different time in the year, right, like when the Earth is back around over here, that's over in this area, that you might actually start to see Leo again. Now just remember, I'm using Leo as an example. I don't really know what time during the year you would actually see Leo, the constellation, but I'm just using this as an example to explain exactly how these travel across the nighttime sky as the year goes on. Hi, so I don't know why, but my video kind of cut out. I think because I pressed the wrong button, to be honest with you. But I just want to go through and make sure that I just touch upon this stuff here. Heliocentric versus the geocentric models. Ancient people thought heliocentric model was correct because we're important, right? We're the Earth. We're an intelligent species. We've got to be the most intelligent things. We're the most intelligent thing on this planet. So everything should be focused around us, right? We're important. But scientists over time, all right, started coming up with, all right, different evidence, all right, Copernicus and Galileo, that showed that no, there's evidence that supports that we are not the center of our solar system. That actually the sun is the center of the solar system, which we know to be true. All right. So these early scientists were looking at different things. For instance, in this paragraph right here, it talks about how Venus went through all of its phases. Right. So just kind of like our moon changes over time. Right. It almost appears like the shape changes. It's because certain areas of the moon are lit up while others are not. Okay. Because the Earth is going around. All right. The Earth is going around. I'm sorry. The moon is going around the Earth. Okay, And when it's in different areas around the Earth, the sun is lighting up the side that's the side of the moon that's facing the sun. And sometimes we see the moon from these different angles. We're going to go into this in the next lessons. So this is kind of a little preview here. I kind of feel like this part of the lesson they jumped in a little too early with this, but anyways, so we see different areas lit up based on the angle which we're seeing the moon, right? Depending upon which side of the where the moon is positioned, all right, around us at nighttime, and how much of it is are we seeing that's lit up. Okay. Now Venus also goes through something similar, right? When we observed Venus through telescopes, we can see that certain areas of it will be lit up and certain areas will not be, as it is orbiting around the sun. Okay. So it goes through these similar phases like the moon. What Galileo was looking at was that Venus would not have this full set of phases just like the moon. It starts at one point, goes through all its phases, and comes back to the point where it originated. It would not happen if the sun was also circling around the Earth. Okay? I gotta at least show you something here. Hang on. Okay, so if we're looking at, for instance, if we have the Earth and Venus and the sun were circling around the Earth, the sun and Venus would always would be in different locations, right? The sun would be moving maybe this way, and Venus would be moving this way, and they may not always be at the same points at the same time. Right now they're both here, and then the sun may be over here, but Venus made it over here, and then when the sun's over here, Venus is over here. So you wouldn't see this nice evenly change in shadows if the sun is what's giving us, all right, these differences in illumination. Okay, the sun and Venus wouldn't be in a predictable pattern that shows a change. So if I'm talking about like the moon, we have a full moon, okay, and then we have, all right. All right, I'm sorry, I'm going the wrong way. 1 second. So if we started off with a mostly dark moon, crescent moon, okay, and then as we move to the next phase, a little more was lit up, okay, and then we move to the next phase, half of it's lit up, move to the next phase, now more than half of it's lit up, and then the next phase, it's all lit up, and then we keep going, and now we're getting a little bit of shadow over here, and we keep going, and now we have, even more shadow, and then we're back to half shadowed, and then mostly shadowed, and then a new moon, and that brings us back. It's a pattern, okay, and it's predictable, okay. We can tell the location of the moon around the planet based upon the phases that we see, okay. And I'll go into what all these phases are and exactly how this works in the next lessons. But we don't, if Venus and the sun were both orbiting around the Earth, we wouldn't see something like this, right, in Venus. But we do. Okay? We do. We see a predictable pattern, or a predictable phase change in Venus. So that was something that told scientists, hey, this heliocentric model cannot work. All right, this can't be what it is. All right, I'm going to leave it there. If you have any questions, please feel free to leave comments, and I'll get back to you as soon as I can. And I wish you luck in this next lesson. All right, so lesson 1. I'm looking in the wrong book. There we go. Lesson 1 in topic 9 is going to be on page right after this, page 437. All right, it's 437. There are 5 questions. Once again, please upload those. Type them in a Word document, upload them, and attach them to your comment, and we're good to go. All right, everybody. You have a great week, and I'll talk to you soon.